So good evening everyone. My name is Avik Mukhopadhyay and I am one of the TAs for this course on digital signal processing. So I welcome all of you to the week number 12 of our live session, which is the last and final week for this course. And if you recall the lectures in week 12, the discrete Fourier transform, or DFT for short, was introduced. We saw the basic definition of DFT and the inverse DFT, and we established the connection between DFT and the DTFT, or the discrete time Fourier transform. In general, we saw that DFT can be thought of as samples of the DTFT. We also looked into the circular convolution, and we saw how the linear convolution is related to the circular convolution, and we concluded that the circular convolution is the same as linear convolution. It's just that it is also periodically repeating the linear convolution. So there is a periodic repetition of the linear convolution, which makes it a circular convolution. That's it. And we also saw the FFT algorithm and so on. So let's start with today's session. So I hope everyone can see question number 1 and 2 on the screen. Let me quickly check the recording is hopefully in progress. So these are true or false questions. We need to determine if these statements are true or false along with the justification. So let's start with the first one. Question number 1 says that the 4-point DFT of the sequence u of n minus u of n minus 4 is 4, 0, 0, 0. We have to state whether it's true or false, and of course justify our answer. So this is a problem based on 4-point DFT, based on DFT computation of a sequence. So let's get started. So it should be pretty straightforward, right? Just formula based. So okay. Alright, so this was the question. So we need to check whether the 4-point DFT of this sequence u of n minus u of n minus 4 is this or not. So let me note it down. So let me put a blank here. Let me put a blank here, so we can so they will be either true or false, right? I'll write the final answer once we numerically work it out. Okay, so let's see. So the sequence was u of n minus u of n minus 4, right? So that clearly we can visualize it graphically, right? So let's do it part by part for our understanding. So let's take the first term which is u of n. Okay, so what does u of n look like? So it starts from n equals to 0, and these values, these heights are 1, right? And it continues. So for every non-zero indices 0, 1, 2, 3, 4, 5 and so on. So the x-axis is in. For all non-negative indices it takes the value 1, and for all negative indices -1, -2, -3 and so on, it is 0. So this is known to us. And the second term was u of n minus 4, right? See, in the question we need to find the sequence, like we need to check for the sequence u of n minus u of n minus 4. So this was the first part, which is u of n, and from u of n we are subtracting u of n minus 4. So let's see how u of n minus 4 looks like. So of course, as you can very well guess now, so u of n minus 4 should start from n equals to 4, right? It's just the right shift of u of n by 4 samples, that's it. So u of n minus 4 should start from here at n equals to 4, and for all higher indices it is 1. Okay, and for all n less than 4, such as 3, 2, 1, 0 and so on, it is simply 0. So I'm not showing all the indices, of course. So these are all zeros. Okay, alright, so this is the stem plot for u of n minus 4. Fine. We need to take the difference now. We have to subtract u of n minus 4 from u of n. So what would it look like overall? So now we are taking the difference. Let me call this as x of n. Let me call this difference between these two functions, two sequences, to be x of n, let's say. So now how does this look like? See, the difference would be non-zero only from 0 to 3 practically, because you see, from n equals to 0 to 3 only u of n is 1, whereas u of n minus 4 is 0. So the difference is 1. In all the other cases the difference would be 0, right? So you'll get something like this. It starts from 0. At 0 you have the value 1. At n equals to 1 you also have the value 1. At n equals to 2 and n equals to 3, similarly you have the value 1. Just give me a second. Alright, yeah, so only for n equals to 0, 1, 2 and 3 this is 1, and for all other indices it is 0. so okay. Now in the question we are required to find the 4-point DFT of this sequence. Okay, so all we need to do is find the DFT of this u of n minus u of n minus u of n minus 4. Okay, and we are denoting this difference by x of n just for a simplified notation. So let me call it by cap x of k. Okay, this is the standard notation that we use for DFT, right? So, and what is the general formula for the DFT transform? So you have cap x of k equals n equals to small n running from 0 to cap n minus 1 x of n times e power minus j 2 pi k small n by capital N, right? And here k runs from 0 to cap n minus 1, right? This is known to us. So in this case, see, go back to the question, we need to find the 4-point DFT. So capital N equals to 4 here, and also in the sequence x of n you see, which is the difference between u of n and u of n minus 4, there are 4 points only. So here cap n equals to 4. So if you put cap n equals to 4 in the above formula, so you can further write it as basically small n running from 0 to cap n minus 1, which is 4 minus 1, so it's 3, upper limit is 3, and this is e power minus j 2 pi k small n by cap n is 4. Okay, and k is running from 0 to cap n minus 1, so 0 to 3 basically. So k is 0, 1, 2 up to 3. This is the DFT. Now all we need to do is put k equals to 0, k equals to 1, 2 and 3 and calculate the coefficients, DFT coefficients, that's it. Okay, and we will have the answer. So let's do that. So if I put k equals to 0, okay, what do I get? Cap x of 0 equals summation running from 0 to 3 x of n, and this term will be e power, basically there will be a term e power 0, right, because k is 0 here. So e power 0 is again 1, so it doesn't really matter. So this will be basically x of 0 plus x of 1 plus x of 2 plus x of 3, right? And what are these values of x of 0, x of 1, x of 2 and x of 3? What is our x of n? Our x of n is this, u of n minus u of n minus 4. See, so it takes the value 1 for n equals to 0, 1, 2 and 3, right? So all of these values would be 1. Okay, so it's 4. Okay, so okay, one coefficient we have calculated. Now let's calculate the coefficient for k equals to 1, so which is cap x of 1. If you substitute k equals to 1 in the formula, so you get this. So now this e power j term will exist actually, because you see it is e power minus j 2 pi k n by 4. So you are putting k equals to 1 now, so you will have e power minus j 2 pi by 4 n, right? So now you have this, and if you just expand it, first term is fine, it's easy because e power 0 will be there, and second term you will have times e power minus j 2 pi by 4, because n equals to 1 you are putting for the second term. Similarly for the third term you have n equals to 2, so this will be minus j pi basically, and the last term would be minus j 3 pi by 2. You can check it. So what do we have? This is x of 0, and e power minus j 2 pi by 4 is basically e power minus j pi by 2. So it is cos pi by 2 minus j sin pi by 2, so it is minus j. Okay, so this is minus j times x of 1, and what is e power minus j pi? It's minus 1, so this is minus x of 2, and what is e power minus j 3 pi by 2? It is equal to j, so you have j times x of 3. Now again put all this, we know the values of x of 0, x of 1, x of 2 and x of 3, they are all 1, right? So put the values. Okay, so just they cancel out. This is 0, second coefficient is 0. Now let's go k equals to 2. You just do similarly. If you substitute k equals to 2, you will get e power minus j pi n, and again if you expand it, so okay, so yeah, all right, so yeah, now just if you put the values of all these complex exponentials, then so the first term would be 1, or let me not do step jump, so e power 0 is 1, so, and e power minus j pi is again minus 1, e power minus j 2 pi is 1, and e power minus j 3 pi is again minus 1. Sorry for this interruption. There's a power cut actually. Just give me a moment. Alright, so let me present this again. Okay, so sorry for the interruption, there was power cut, so let's continue from here. Yeah, so we were calculating this k equals to 2 case, the coefficient. So what will be this last term here? So e power minus j 3 pi is again minus 1, so we will have minus x of 3. Now just put 1. Again, see, all of them get cancelled, so they cancel each other and we get 0. Lastly, you take k equals to 3, because k goes from 0 to 3, right, up to 3. So the last coefficient would be capital X of 3 this would be e power minus j 3 pi n by 2, and so you get this. I'm again just putting the values of these complex exponentials. This is 1 plus j minus 1 minus j. Again you see they cancel each other, so we have 0. So what did we get? So we got, therefore, capex of 0 we got 4, capex of 1 was 0, and capex of 2 we got 0, capex of 3 also we got 0. Hence DFT of x of n, and what is our x of n? We actually assumed u of n minus 4, which was the given sequence. We assumed it to be x of n. So, and the DTFT of this sequence happens to be 4, 0, 0. See, capex of 0, capex of 1, capex of 2, and capex of 3. That's it. And this is exactly if you go back to the question, this is exactly what was mentioned in the statement. See, 4, 0, 0. So this statement is actually true, right? So therefore true. So I'll go, remember I left a blank space. Yeah, here. So I'll write here okay, and this is actually the justification or the proof, whatever you like to call it. Okay. Alright, so first question is done. Now let's check the second one. It's also true or false. So it says that let x of n be a finite length sequence of length capital N. The n point circular convolution of x of n and delta of n minus L is this, which is x of n minus L modulo cap n. So this symbol is actually this symbol in the right corner. So this symbol is actually x of n minus L mod n. Basically, you have like what did I say? Angular brackets on the edges. That denotes basically, if you recall the lecture notes also, we use this notation, and this suffix cap n is basically indicating mod n. Okay, why? Because this is periodic, so for periodic sequences we use this kind of notation, and this statement is clearly true actually, because you don't even need to calculate it explicitly as such, because what do you know about circular convolution? So in the starting of today's session also, I while giving you a recap of the contents, I mentioned that circular convolution is the same as linear convolution, but it's just that it's a periodic repetition of the linear convolution, and our periodicity is capital N. So you see, when you do linear convolution of these two sequences, given sequences, which is x of n and delta of n minus L. So delta of n minus L is the impulse, right? Shifted impulse, that's it. whenever you convolve any sequence with the impulse response or delta n, not response, impulse function delta n, you get the exactly same function, right? And in this case, if you convolve x of n with delta of n minus l, you would get x of n minus l, right? This is the linear convolution. And now the point which I mentioned, circular convolution is same as linear convolution with an additional constraint that it has to be a periodic repetition. So in order to ensure that constraint for periodic repetition, all we are doing is making it mod n. Okay, so this is notation, x of n minus l mod n, that's it. So this is actually true. Okay, so let me go to a fresh page. Yeah, so second one again. So we concluded, right, this is true. And now coming to the justification which I dictated verbally. So if you perform the linear convolution, of these two given sequences, x of n and delta of n minus l, you get x of n minus l. There is no periodicity coming into the picture yet. So, and now we know that circular convolution is the same as taking the linear convolution and periodically repeating it with period cap n. So is repeating spelling correct? I am not sure. I think it's REPA. Maybe I'm not sure. Okay. So yeah. Alright, so based on this, we can now write the circular convolution as the notation is like this. So we have a circle which is enclosing the star, which denotes the circular convolution operation, and we will have exactly the same output as that of linear convolution, except that this is exactly in x of n minus l, except that it is now modulo cap n to make it periodic. Okay, this thing here, it's the periodic repetition of linear convolution. Okay, so this is true, this is indeed true. And this notation, this actually means n minus L mod cap n. Okay, you should already know this, but still I am writing for those who are not familiar. So that's it. Or else you can go formula wise also, like so this is one way, this is one method, and also by the numerical definition of circular convolution, you know that the circular convolution of these two will be the first sequence x of n will remain the same, only the index will go from change from n to k. Second one will again get flipped and then shift by n, so it's basically n minus L minus k, that's it. But here along with that we'll have this mod n. Okay, and here n runs from 0, 1, so on up to cap n minus 1. And if you see this term here, this is this summation, basically it is non-zero only for k equals to n minus L, because then only this impulse function will take the value 1, otherwise it is 0. So yeah, so ultimately what you will get is x of this. So this is another way of looking at it, but the straightforward way to actually observe is the fact that circular convolution is nothing but the linear convolution, periodic repetition of the linear convolution, that's it. So you can straight away just conclude that this is true. So that's it. Now moving to the third question. Okay, let me check if okay. Alright. Now okay, this is the third question. So we have been given two finite sequences. First one is denoted by x, and its elements are the sequence is x of 0, x of 1, x of 2, and x of 3. Okay, there are 4 indices. Okay, it's a length 4 sequence, and similarly another sequence is there, small h, it is also length 4 sequence, and their corresponding DFTs are denoted by capital X and capital H, and we have the exact coefficients also. For cap X we have 1, j, minus 1, minus j as the DFT coefficients, and similarly for cap H also it's written. Now given this information, we need to use the properties of the DFT to compute the following given in A, B and C parts. and it is mentioned that do not compute x and h explicitly. We no need, there's no need of calculating these sequences, like taking the there's no need of finding the inverse DFT in order to compute x and h, the time domain sequences. There's no need to do that. Using just properties of the DFT itself, you need to compute the following. So in part A, you need to find the DFT of this sequence x of 3, x of 0, x of 1, x of 2. Okay. And similarly in part B and C also, you are asked to find similar kind of things. So let me first, hopefully this question is clear, right? So the idea here is to use the properties of the DFT. Okay. Hopefully if you are able to see, like from the questions from part A, part B and part C, if you are able to see some kind of pattern in the questions, in the sequences in part A, part B and so on, then you might be able to predict which property might be used here. So anyways, let me first note it down. I hope the question is clear. The language is straightforward. So let me write here only. So we are in the third question. There are two finite sequences. First sequence is this, and we are using small lowercase alphabets for the time domain sequences and the upper cases for their DFTs. Okay. Alright. Another one is and their DFT is this. Okay, so this is given, and again if you see, these finite sequences are of length 4. So obviously here capital N equals to 4. Okay. Alright. So this is given, and based on this you need to find okay, let's start with part A. You need to find the DFT of this sequence x of 3, x of 0, x of 1, x of 2. Okay. Now you see, so you have been asked to find the DFT of this x of 3, x of 0, x of 1, x of 2. This is what you need to find. Now you already know the DFT of this small x, this original sequence here. Okay, I am showing a tick mark beside it. So the DFT of this x of 0 comma x of 1 comma x of 2 comma x of 3, that you know, that is capital X and its coefficients are known to you, 1j minus 1 comma minus j. But now you see, now you need to find the DFT of another sequence. So this is the sequence basically, which is similar to our original sequence small x. The only difference is that the order is not maintained. See, previously the order was in like a proper ascending order, x of 0 comma x of 1 till x of 3. Here you see the pattern is different, the order is different, order of the sequence, and the main thing is to actually find that pattern, observe that pattern. Okay, what is the order? Is it following some special pattern? That's all that you need to find. Once you discovered it, you are done. You are done with the problem. So in case you are able to decode that pattern, great, that's great. You can pause the video also and also try to find like the relation between these and this sequence, these two sequences. What's the pattern? So if you see what's the what should I say, what's the relation between them? Okay, so if you observe carefully, the second sequence, which is shown in red, x of 3 comma x of 0 comma x of 1 comma x of 2, is nothing but a right cyclic shift of the first one. See, all this, the original sequence, which is x of 0 comma x of 1 comma x of 2 comma x of 3, if you shift all these individual elements to the right by one place and you shift this cyclically, why this is a cyclic shift? Because here we are dealing with DFT and there is concept of periodicity. It's a length 4 sequence, so this basically means that it repeats this sequence x of 0 comma x of 1 comma x of 2 comma x of 3. Once you reach x of 3, then again the following element would be x of 0 again. So again x of 0, x of 1, x of 2, x of 3, again x of 0, x of 1, x of 2, x of 3, and so on. So that's the thing. So that's why, like, when you shift it to the right, so x of 3, if it goes to the right, it will basically come back in the first place, which is exactly what is happening here. So x of 0 was previously in the first place, it now goes to the second place. Similarly, x of 1 was in the second place, it now goes in the third place. X of 2 moves from third place to fourth place, and x of 3 moves from last place to the first place. So that's a cyclic shift. Okay, so that's the thing to observe. And once you express the new sequence for which you need to compute the DFT as a shift of the previous sequence, original sequence, then you can easily use the shifting property of DFT that is well known to you. Okay, in DTFT also we saw shifting property. Shifting in the time domain sequence leads to a exponential multiplication, right, in the DTFT, and same holds for the DFT as well. So let's do that. Okay, so this is clear, right? Okay, so we're looking at part A, DFT of this is what we need to find. Okay, so remember previously we originally had what sequence? We had this. So you see all of them, they are getting shifted, see, and x of 3 will come back again, it will come back to the first place, okay, because it has to like be periodic, that's why. So that's why I am using the more convenient term, which is cyclic shift. Okay, right, cyclic shift. By one sample. So that's it. So you can write this as DFT of, you have the original sequence, you shift it and do mod 4, okay, mod cap n, because cap n is 4 here, so you do this, that's it, for the periodicity constraint. And now what is the DFT of this thing? This is the shifting in time domain, so leads to exponential multiplication in the DFT, in the frequency domain. So this will be e power minus 2 pi k by 4 times cap x of k, because you just recall this property, if we have a shift by, let's say, L samples, sorry, okay, then its DFT was e power minus j 2 pi k L by cap n times x of k, okay, this was the property. And here cap n is 4, okay, that's known, because sequences are of length 4, and this L here, this shift here is basically 1. You see, we need to find DFT of x of n minus 1 mod 4. So from this property we are actually getting this. And what is this e power minus j 2 pi k by 4? Firstly, what is e power minus j 2 pi by 4? It's basically e power minus j pi by 2, which is minus j. So this is, and it is raised to the power k, so minus j to the power k times cap x of k. And remember, k runs from 0 to cap n minus 1. Here cap n is 4, so 0 to 3. That's it. This is the DFT. And now all you need to do is just put the values of k from 0 to 3 and find these DFT coefficients. So let's do that. So for k equals to 0, what do we have? This term here, minus j to the power k times cap x of k, that becomes minus j to the power 0 cap x of 0, and so this is 1 times, what is cap x of 0? Okay, so let me not use cross for multiplication here, because you might confuse it with cap x. So let me use this dot, okay, for multiplication. So minus j to the power 0 is 1, that's fine. What is cap x of 0? Cap x of 0, if you go, the DFT cap x is already given in the question. DFT of small x, which is cap x. So these are the coefficients 1 comma j comma minus 1 comma minus j. So here cap x of 0 is 1, cap x of 1 is j, cap x of 2 is minus 1, and cap x of 3 is minus j, like that. So cap x of 0 is, from this sequence if you observe, it is 1. So this is 1 times 1, which is 1. Okay, now for k equals to 1, you have minus j to the power 1 times cap x of 1, which is minus j times, what is cap x of 1? What was the second element? It was j. See, it was j. Minus j times j. Now for k equals to 2, you have this, and what is minus j to the power 2? It is minus 1 times cap x of 2, the third element of the DFT, which is minus 1. So overall it is 1, and finally for k equals to 3, you have this, and minus j cube, minus j whole cube is j, and cap x of 3 is what? The last element of the DFT, which is minus j times minus j. So this is 1. Alright, so overall the DFT of the sequence given in our question, which is this, is, see, all the coefficients are 1, all the 4 coefficients are 1. So this is our answer for part A. Okay, so part A is done. So we have not, see, the constraint which was given in question is that we should not compute small x and small h explicitly by taking IDFT or anything. We just use the properties of DFT, that's it. All we did was we made an observation carefully that the given sequence is nothing but a right cyclic shift of the original sequence, and then we use that shifting property of DFT, that's it. Okay, alright. So part A is done. Now let's move to part B. What is asked in part B? Okay, part B, in part B we have to find again the DFT of this sequence, which is h of 0 comma minus h of 1 comma h of 2 comma minus h of 3. And again, see, in part A basically there was a connection, there was a relation between this sequence, given sequence, and our original sequence small x. Similarly in part B also there is some kind of a relation between the given sequence, which is h of 0 comma minus h of 1 comma h of 2, then again minus h of 3, and our original sequence, which is small h. See, it's exactly the same. Here the sequence, the order is same, except for the fact that there are alternate signs. See, for the first term we have positive sign h of 0, for the second term we have minus sign in front of h of 1. Then again we have positive sign, and finally we have a negative sign in front of h of 3. So we have alternating signs, that's the thing. So how can you write that? If you just multiply with minus 1 to the power n, where n is your like small n, which is the running index, then you can actually incorporate this alternating sign thing. So whenever the indices are odd, you'll have a negative sign, and whenever the indices are even, you will have a positive sign, which is exactly what is happening here. So let's do that. So we need to find DFT of this sequence. So minus sign. Okay. So now let me write it as in a different form which I was dictating. So what I was saying is that we can also write this in a more compact form like this. Isn't it? We can do this, right? Because if you choose, like, if you vary small n from 0 to 3, this is exactly what you get. Okay, for even indices you get positive sign, and for odd indices you get a negative sign. That's it. And now you can write this minus 1 to the power n in a different form as well. If you can cleverly, manipulate this term minus 1 to the power n and express it in some form of complex exponential, then you can go ahead and use the properties of DFT. Because remember, at the end of the day we are asked to use the properties of DFT to find the DFT of the given sequence. We need to use some properties, and here it involves multiplication by minus 1 to the power n in front of the sequence. So we don't directly see any such property that could be used in this case till this point, because we don't actually have any such property where we have minus 1 to the power n times h of n, and then we can directly take its DFT and relate it with the DFT of the original sequence h of n. At least it is not directly visible at this stage yet. So for that, the idea which I told is to express it in terms of some complex exponential multiplied by some complex exponential instead of minus 1 to the power n. Okay, and actually there is a complex exponential hidden in this minus 1 to the power n also. That is, what is that? If you have to express it in form of some e power j, some 2k pi by n form, what would be that? So you can write minus 1 to the power n as e power j pi n, isn't it, times h of n. This is fine, right? E power j pi n is nothing but minus 1 to the power n, and so e power j pi n, and again I am just converting it into the standard form, which is e power j 2 pi k n by cap n. Okay, so you can write this as per j 2 pi times 2 by 4, cap n is 4 here, times cap small n in the numerator, and each of n is there. Okay, now you see, now this is in a form where we can now use the property of DFT. Particularly which property? When we have a multiplication by complex exponential in the time domain, and then we can take its DFT, and we have the relation that will actually basically shift the DFT. That's it. So it's just the opposite of what was happening in the previous part of this question, right? In the previous part we had shift in the sequence itself, like in the time domain, and then we were getting the output as the DFT, which was scaled by a complex exponential, and here we are actually scaling the time domain sequence by a complex exponential. We are multiplying it, and that will lead to a shift in the DFT. That's it. So the transform, so this will give us, and the shift will be this 2 here, sitting here, this term. This will be the shift. So it will be h of k minus 2, and again mod 4 will be there because of periodicity. Okay, so this is h of k minus 2, and why? Because of this property, which is as follows. So if you have some e power j 2 pi l n by cap n multiplied with x of n, its DFT is given by cap x of will be, so this will incur a shift by L unit, so L sample, so k minus L. Originally the coefficients were x of k, right, cap x of k, that will get shifted by L units. Okay, and again this is mod cap n. So this is the property. Alright, and so this is again, this is like the right cyclic shift of the DFT, original DFT cap h of k by 2 units. That's it. So remember what was the original DFT cap h? This was 0, 1 plus j, 1, 1 minus j. You just do right cyclic shift of this sequence, this DFT, by 2 samples. So basically 0 will now, which was previously in the first place, will now go to the third place. Correct? 1 plus j, which was sitting in the second place, will now go to the last or the fourth place. Similarly 1, which was sitting in the third place, will now come in the first place because it's a right cyclic shift by 2 units. See? So that's it. So exactly following that, you will get this sequence. So this is the Okay, all right. All right, so part B is also done. Okay, now coming to the third part of this question, we need to find the DFT of the circular convolution between small h and small x. So this notation here, like cross bounded by a circle or a cross inside a circle, this symbol here denotes the circular convolution. So what will be the DFT of the circular convolution of h and x, that we need to find. Now for this you don't need to find first h and x and then take their circular convolution and then find the DFT. That's not how you do it. It will become too much lengthy and complicated. That is the thing. You see, the process is not to do all the computations explicitly. That's what is mentioned in the question. It is the properties of the DFT which make our life easier. Just by simply using the known properties, we can just answer within 1 or 2 lines. That's it. So here also we'll try to do the same. So this is part C, and we need to find DFT of h circularly convolved with x. And here I am using this kind of a notation, like, so it's a star kind of thing, asterisk inside a circle, which is I believe the notation that we were using in the lectures also, right? So I'll stick to that only. In this question the notation is a slightly different one. It looks like a tensor product, like a cross inside a circle, but here it's almost the same, just a different one. So this is circular convolution. Okay, let me write it also. This is circular convolution. All right. So yeah, now tell me, how can we simplify this? So remember, like, convolution, a particularly circular convolution in the time domain, here we are analyzing DFT. So circular convolution in the time domain will translate to simple multiplication in the DFT domain. So basically, if you have this, like, how should I say it? So you know this h has the DFT this, okay, x has DFT this, cap x, okay. What about this? What about the DFT of this circular convolution of small h and small x? Circular convolution in time domain will translate to simple multiplication in DFT. So this is just multiplication. That's it. See how simple it is. So it is simply the product, the multiplication of the individual DFTs. So this, and what was our cap h DFT of the h sequence? It was 0, 1 plus j, 1, 1 minus j. Okay, I'll write that 0, Just a second. Yeah, it was 0 comma 1 plus j comma 1 minus j. So this is h of k. Times what is cap x of k now? Cap x of k is this. So 1 comma j comma minus 1 comma minus j. One comma j comma minus 1 comma minus j. So we need to take, like, perform the pointwise multiplication. It's like a dot product or inner product of two vectors of length 4. See, so what will be the pointwise multiplication? So first we have 0 multiplied with 1. We are multiplying the first elements of these two vectors. So this is 0. Second term you will have 1 plus j times j, which you can write it as minus 1 plus j. Third term will be 1 times minus 1, which is minus 1. Fourth term would be 1 minus j multiplied by minus j, which you can also write as minus 1 minus j. Just verify that. Okay, so that's it. So third question is also done. Okay, now let's move to the fourth question. So yeah, recording is going on. Alright. Yeah. Okay, so this is the fourth question. So it is given that there are two finite sequences, small h and small x, which have the following DFTs. So cap x is the DFT for small x, which is 1 comma minus 2 comma 1 comma minus 2, and capital H is the DFT of small h sequence, which is 1 comma j comma 1 comma minus j. And again here y denotes the circular convolution, specifically the 4-point circular convolution, because of course here the capital N is 4 because x and h are length 4 sequences. So y, which is the 4-point circular convolution of small h and small x. And again we have to use the properties of the DFT. We need not compute the time domain sequences x of n and h of n explicitly. We don't need to use any IDFT or anything without computing them. Just merely by using the properties of DFT, we need to solve part A and part B. In part A, we have to determine DFT of x of n minus 1 mod 4. So again you see it's quite similar, because here so what this means is that we have to do the right cyclic shift of x of n. See, and then take its DFT. That's it. And similarly for this DFT of h of n plus 2 mod 4, we have to take the left cyclic shift by 2 samples and then take the DFT. That's it. So let's do that. and then we will come to part B. So let me first note it down. Okay, okay, these DFTs are given. These are given, and this denotes the 4-point circular convolution. Okay, so clearly here n is 4. Alright, so in part A we need to find the DFT of this. Okay, so again you use that property whenever there is a shift, time shift, its DFT will be the original DFT scaled by a factor of e power minus j 2 pi k times the shift amount by cap n. So that property. Okay, so if you use that property, you will get this as e power minus j 2 pi k by 4 times x of k. So again, if I have to write the property, let me again write it for you. So property was like this. So this was the property, okay, which we have used here, and again this e power minus j 2 pi by 4 is minus j, and that has to be raised to the power k. So this is simply this. Okay, and now here k runs from 0 to cap n minus 1. So cap n is 4, so k runs from 0 to 3. So you take first, put k equals to 0 and calculate the coefficient. So that gives you j power 0 times capex of 0, which is 1 times capex of 0 is what? Just look at this sequence capex. At the 0th index, it is the value 1. Okay, so capex of 0 is also 1. 1 times 1 is 1. Okay, now check for k equals to 1. So we will have minus j to the power 1 times capex of 1, which is, so this this is minus j times, what is cap x of 1? What's the second element? It is minus 2. Okay, so this becomes 2j. Sorry, this k equals to 2 now. So this is minus j to the power 2 cap x of 2, which is minus 1 times, what is cap x of 2? It's the third element basically, third coefficient, which is 1. This is minus 1. And finally, for k equals to 3, we have is minus j raised to the power 3 is j, and cap x of 3 is the last element, last DFT coefficient, which is so minus 2. Minus 2, so it is minus 2j. So therefore DFT of this shifted version is 1, 2j, minus 1 and minus 2j. Okay. So that's it. And now again we have to do similarly for DFT of h of n plus 2 mod 4. Again the same process will apply here. So okay. So this again, using the same old property, we can write this as this. And what's the property? Again, it's always a good habit to mention the reason or the justification or whichever property you are using whenever you are performing a step. Okay, so again the property was like this. Transform would be right. This is the property. So you see, in general, when you have shift by n minus L, okay, then you have e power minus j 2 pi kl by cap n, and here we have n plus 2. The shift is like on the left side, so you will have e power j, some like positive coefficient will be there, though, so that negative sign will not be there, right? So this is nothing but e power j pi k capital H of k, and again e power j pi is minus 1. We already have a k here in the exponent, so it is minus 1 to the power k. Okay, and again just there also k runs from 0 to cap n minus 1. Cap n is 4, so 0 to 3. Again you take k equals to 0 first, so this coefficient becomes this, which is 1 times what is h of 0, I mean cap h of 0. Cap h is this sequence. So the first at index n equals to 0 or k equals to 0 rather, we have the value 1. So cap h of 0 is 1. Okay, for k equals to 1 you have minus 1 to the 1 cap h of 1, which is minus 1 times cap h of 1. What is cap h of 1? Is the second element of the DFT, second coefficient, so it is j. This is j, this is minus j. Okay, okay, equals to 2, we'll have this. So minus 1 raised to the power 2 is 1 times cap h of 2 is the third coefficient, so which is 1. Okay, and finally for k equals to 3 you get minus 1 times what is cap h of 3. Cap h of 3 is the last coefficient, last DFT coefficient, which is minus j. So this is j. Okay, so that's it. Therefore the DFT of the sequence, the left cyclic shift by 2 samples which was given, this is 1 comma minus j comma 1 comma j. This is the DFT. Okay, so part A is done. Now coming to the part B, we need to determine small y of 0 and small y of 1. So basically small y is what? It's the 4-point circular convolution of small h and small x. So we need to evaluate that 4-point circular convolution at 0 and 1. That's it. Okay, so you might think like in this case you have to find the circular convolution first, because you need to find the like value of the circular convolution at some time instant, like at 0 and k, right? At 0 and at 1. For that you might think like, okay, let me first find the general expression for pi of n, and then I will put n equals to 0 and 1 and then get the values. But instead of that, let's restrict ourselves to using the properties of DFT, which actually will make our life simpler. So another way we can approach this problem is that, see, we need to find small y of 0 and small y of 1. Fine. Okay. So since small y is the circular convolution of small h and small x, and again, as I mentioned before, circular convolution in the time domain translates to simple multiplication in the DFT, in the transform. So if we have small y equals to small h circularly convolved with small x, then you can write, when you take its DFT, it becomes capital Y of k equals capital H of k multiplied by capital X of k. That's it. So instead of a complicated operation like a circular convolution, you just moved to simple multiplication, which is really simple, right? And now this is the expression you know for capital Y of k, which is the DFT of y. And capital Y of k, you just now got that it is the product, it is simple multiplication of capital H of k and capital X of k. Capital H of k is known to you, it's the given sequence, it's known to you. Capital X is also given, it's the DFT of small x. These two are given, these two DFTs are given in the question. You can easily take the pointwise product and find capital Y of k. That's it, you can do it. But you are asked to find small y of 0 and small y of 1. For that you can take the IDFT. In order to go from capital Y of k to small y of n, you need to just simply take the IDFT, inverse DFT, that's it. And just find the IDFT at these 2 points, 0 and 1, that's it. So we will just do that. Okay, this will be very simpler. When we actually solve it, it will be actually much simpler than what I might be sounding right now. So let me so we are in part B. Okay, so the idea which I used here is, my handwriting is just horrible. So okay, this is the circular convolution, right? So this implies capital Y of k is capital H of k times capital X of k. Simple multiplication. And now recall that small y of n is nothing but the inverse DFT, IDFT of capital Y of k. Okay, and if you recall the formula of IDFT, it is 1 by cap n, k running from 0 to cap n minus 1, capital Y of k times e power j 2 pi k small n by cap n. This is the formula. And here what's the size of the TFTs? They are four length sequences, right? See, in the question there are 4 points only. Cap n is 4, which is why this small y, which is the 4-point circular convolution of small h and small x. So cap n is 4 in our problem. So now this you can further write as 1 by 4 k running from, just putting cap n equals to 4, that's it, times e power j 2 pi k n by 4. Fine. Now you just, in the question, you see the question, you need to just find small y of 0 and small y of 1, only these two. You don't have to find all the points for all the points. So for that, just put n equals to 0 first. So y of 0 would be 1 by 4 k running from 0 to 3 capital Y of k times e power j. So this term will be basically 0 here, because small n is 0, so overall it will be simply 0, correct? So this is basically 0. This is e power 0. This is e power 0. So it's simply 1 by 4 times capital Y of 0 plus capital Y of 1 plus capital Y of 2 plus capital Y of 3. Okay. Now what are these capital Y of 0, capital Y of 1? See, in the first line here, I am underlining this line. We have already written that capital Y of k is simply the product of the DFT coefficients of capital H and capital X, right? So just use that. So if you put k equals to 0, you get capital Y of 0 is nothing but capital H of 0 times capital X of 0. And similarly for other values of k also, you can just take the product, that's it. So you just do that, and so you get Y of 0 as 1 by 4. What is capital Y of 0? It is, like we saw, that simply the product of capital H of 0 and capital X of 0. Similarly, what is capital Y of 1? It's the product of capital H of 1 and capital X of 1, and again for the other terms also. We'll have this, okay. Let me actually, we are using first bracket here, so stick to that, okay. So this is our Y of 0, and now just put these values, okay, put these values. So capital H of 0 and capital X of 0. So see, so we need to take the first elements of these TFT coefficients and then multiply. So the first elements are 1 and 1 each. Okay, both of them are 1. So it's 1 times 1 plus now capital H of 1 times capital X of 1. So you have to take the second elements from the two vectors and multiply them. So it is minus 2 and j. Okay, so j times minus 2 plus now the third element, pointwise multiplication of the third element, again both are 1, so plus the last, so minus 2 and minus. Okay, so what do we have? This is 1 minus 2j plus 1 plus 2j. So minus 2j and plus 2j gets cancelled and we'll have 1 plus 1. So 2. What are 2 will survive, and so this is the thing. Okay, so this is the value of y of 0. So this is y of 0 we got, and now also we need to find y of 1, right? So again just follow the same thing. In this case we put n equals to 0, and now to find y of 1 we will just put n equals to 1 in the IDFT equation. So now putting n equals to 1, we will have y of 1 equal to 1 by 4 k running from 0 to 3 capital Y of k times e power, you go back here, so e power j 2 pi k, now n is 1, so 2 pi k by 4. Okay, right. So this is equal to 1 by 4 times first you put k equals to, you just expand this, put k equals to 0 first, then k equals to 1, then k equals to 2, then k equals to 3, yeah, you should get this, and you just now again y of 0 is nothing but h of 0 times x of 0, you just use that, same for the other coefficients of y, you just do that. So again e power j 2 pi by 4, what is that? It is equal to j, and y of 1 I am writing as h of 1 times x of 1, and what is e power j pi? It is minus 1. Okay, and what is e power j 3 pi by 2? It is minus j, so minus j times y of 3, which is again h of 3 times x of 3. Okay, and if you just substitute these values, you get first term will be first term will be basically 1 times 1, and second term will be plus j times minus 2. Third term will be, so okay, we already have a negative sign here, so this is minus 1 times 1, and last term will be minus j times minus 2. Okay, and overall, so this 1 and 1, the first and third terms cancel each other, and only this second and fourth terms, they will combine together and survive. So we will actually get, what is j times minus 2? It is 2. And similarly for the fourth term also it's the same, so it's 2 and 2 together becoming 4 with a 1/4 scaling factor sitting outside, so you get 1. So this is y of 1. So therefore y of 1 equals to 1. So you calculated both the required values. Y of 0 was half and y of 1 is 1. Okay, that's it. Question number 4 is done. Now coming to the final question of today's session. So again, given in the question is a finite sequence small x having a DFT denoted by capital X, which is this sequence 0, 1 plus j, 1, 1 minus j. Again it's a 4-point DFT, and so capital N equals to 4 here, and so these are the coefficients basically. Capital X of 0 is 0, capital X of 1 is 1 plus j, capital X of 2 is 1, and capital X of 3 is 1 minus j. This is given, and again we have to make use of the properties of DFT to determine the DFTs of the following functions given in part A, B and C. Okay, and you clearly see in part A we have y of n equals to e power j pi by 2 n times x of n. So see, it's directly you can just use the property of DFT. See, we have a exponential multiplication in front of the time domain sequence, so it will translate to a shift in the DFT transform basically, right? So let's just do that. Okay, let's first solve the part A. So given this DFT, okay, so clearly capital N is 4 here. We will be looking at first part A. This is the given sequence. Y of n is e power j pi by 2 n times x of n. We need to find the DFT of y of n. So now all we need to do is further slightly modify this form. So it's e power j pi by 2 n, the multiplicative factor. We need to express it in the form of e power j 2 pi k n by cap n, that form. Okay, here cap n is 4, so we can also write it as 2 pi by 4 n times x of n. See, now you have expressed in the denominator is 4, so which is cap n, in the desired form you have expressed. And now just simply use the DFT property, that's it. So DFT of e power j 2 pi by 4 n x of n is nothing but the original DFT x of k shifted by 1 unit or 1 sample. So since y is this, again let me write the property. Which property have we used here? The property is this: e power, whenever you multiply a complex exponential, 2 pi some L times n by cap n, whenever we multiply this to x of n, the corresponding DFT will be the shifted version of the original DFT by L units. So here L, the shift is the L, the amount of shift is L. So comparing these two forms, here L is basically 1. So therefore the shift occurs by one unit here. Okay. So yeah. So that's it, you are done. So now you already have the DFT, right? Capital X, you have the coefficients, you just need to do the right cyclic shift of those DFT coefficients. That's it. So this is simply the right cyclic shift of cap x of k by one sample. Okay, so this is the given one: 0, 1 plus j, 1, 1 minus j. So 0 was in the first place, it moves to the second place now. 1 plus j was in the second place, it moves to the third place now. 1 was in the third place, it now moves to the right, so it now comes to the fourth place. And 1 minus j was in the fourth place, so it comes back and sits in the first place now, because it's a right cyclic shift. So you will get 1 minus j, 0, 1 plus j, 1. That's it. That's the DFT. So yeah, so this is all what was asked in part A. So part A is done, and similarly for part B also, you see we have cos pi by 2 n multiplied with x of n, and again as you might have figured out already, the key step here is to, so it involves just an additional step here in part B, just to express cos in terms of the exponential, and we are very much familiar with the formula that cos of theta is e power j theta plus e power minus j theta whole divided by 2. So once we use that formula, we can express this cos in terms of the complex exponential, and then again make use of the same property which we did for part A and find the DFT. So that's exactly what we are going to do. Okay, so part B, we have cos pi by 2 n times x of n, and this is nothing but half e power j pi by 2 n x of n plus half e power minus j pi by 2 n x of n. Okay, and again, like in the previous part, we moved from e power j pi by 2 n to, we converted it into e power j 2 pi by cap n, that form 2 pi by 4 times n. Okay, so that we are in the desired form before using the property. So just doing that, so this is half e power j 2 pi by 4 times n times x of n plus half e power minus j 2 pi by 4 n times x of n. Okay, and now just simply by linearity we can find the DFT of this overall linear combination. Okay, so this will be for the first term. Okay, wait, for this term the DFT will be right cyclic shift of cap x of k by 1, and for the second term here, since it involves the e power minus j term, so due to the negative sign it will be left cyclic shift of cap x of k by 1. The shift amount is 1 in both cases, and so yeah, so this scaling factor of half, it just comes out as a constant in both the cases, and we have, for the first term we have right shift, so right shift means k minus 1, and similarly for the second term we have left shift, so it is k plus 1. Okay, So I should write actually undergoes this, undergoes, and similarly this undergoes. Okay. So again, if you right cyclic, do the right cyclic shift of x of k given DFT sequence, this 0 comma 1 plus j comma 1 comma 1 minus j, you will get, so this half factor is there anyways, you will get 1 minus j comma 0 comma 1 plus j comma 1, and on doing the left cyclic shift you will get 1 plus j 1 1 minus j 0, and on adding them together you will get 1 comma half comma 1 comma half. Just verify. Okay, so that's it. So we are done with part B, and lastly for part C. See, in part C, the sequence, the time domain sequence x of n is shifted, right cyclically shifted by 1 unit. So that will basically on taking its DFT, it will go to the original DFT, which is cap x of k multiplied by e power j, that 2 pi k l by cap n thing, right? So here the DFT will undergo a complex exponential multiplication. Okay, so we'll use that property here. Okay, alright, so we are looking at part C now. So y of n is x of this. Okay, so DFT of this thing is nothing but, as I said, there will be an exponential multiplication once you take the DFT, e power minus j 2 pi by cap n, which is 4, times the shift, which is 1 unit, times k. So this times x of k. Okay, again for clarity, let me again write the property. Is the same property that we are using. So property that we have used here is and here actually I have not used this angular brackets before the mod actually. So this implies mod actually. So this actually, the term here is implying n minus 1 mod 4. Okay, in the lectures this angular brackets were used, but I'm skipping them here. So this goes to e power minus j 2 pi k l by cap n cap x of k. This is the property that we are making use of. And again, e power minus j 2 pi by 4 is nothing but minus j, and we have an additional factor of k in the exponent, so it is minus j power k times cap x of k, with k running from 0 to cap n minus 1. Here cap n is 4, so k runs from 0 to 3, Okay, now you just, so what will be the coefficients? You just put k equals to 0 first, then you put k equals to 1 first, okay, then you put k equals to 2, and finally you put k equals to 3. So this will be the DFT. So this is minus j to the power 0 is 1, and what is cap x of 0? Cap x of 0, the first elements, first coefficient is 0 given in the question, so this will vanish. What about this second term? Minus j to the power 1 is minus j, okay, this is minus j times cap x of 1. What is cap x of 1, which is the second coefficient basically? It is 1 plus j, okay, so this is times 1 plus j. Now the third coefficient will be minus j raised to the power 2 is minus 1 actually, times cap x of 2. What is cap x of 2? Is the third coefficient, which is 1. So this is also cap x of 2 is 1, and the third one, so minus j whole to the power 3 is j times cap x of 3. What is cap x of 3? The last coefficient, which is 1 minus j. So this is 1 minus j. Okay, so it is 0, and if you just multiply this together, you will get 1 minus j. This is minus 1, and this is, you will get, on multiplying you will get 1 plus j. This is the DFT. Okay, so yeah, so that's it. We have reached the end of today's tutorial session, and this actually concludes the contents for the entire course. So this was the last week, and hopefully the problems were easy to understand, and the solutions should be straightforward to understand. So you can mail me in case of any queries or anything, or and there's a probability that we might have an additional doubt clearing class or session on the upcoming week, next Monday, same time, 6 p.m. to 8 p.m. Anyways, I think that will be communicated to all of you via email or something. So yeah, but anyway, so so thank you for being part of this final session, and yeah, let me stop the recording. So thank you.